Hello everyone, in this video I'm going to talk about multiprocessing in Python. Multiprocessing is another way to run multiple processes concurrently, just like multithreading. However, unlike multithreading in Python, multiprocessing will have true concurrency. This is because separate Python processes will be created. They will not be restricted by the global interpreter lock. This is because we are technically using subprocesses instead of threads. This makes multiprocessing best for CPU-bound operations like calculations, data generation, and so on, whereas multithreading is best used for IO-bound operations involving things like files and networking. Now let's jump into some examples. Now if you've seen my multi-threading video, then you're likely going to recognize all of the code in these examples because it's pretty much the same stuff except I'm using multiprocessing instead. So let's start with our first basic example where we're just showing off the very basic use of multiprocessing. So let's start off with the modules imported. Really the only important one is multiprocessing because that's what you need to actually start processes in Python, but I'm going to explain what the other stuff is for. So Colorama is for coloring text. It allows you to have really pretty text in the command line. OS is just so I can use the get PID function so that I can get the process ID of each process that we start. And time is so I can use the sleep function because I'm going to need that in order to be able to show you how the program is running concurrently. Because even with multiprocessing, given how simple this function is, you're not really going to get to see the concurrency being played out here. It's going to still look like it's been running linearly. So using the sleep function will help see the concurrency with the processes. So we've got two functions, process count and main. Process count is the function that we're going to run in our separate processes. What it does is that it will first print out its process ID in red, as you can see here, and then it's going to print out the name, say it started, and then it's going to count up to the number that we pass into it as count until it reaches the end. So in this example here, I pass in 10 for the count. So it's going to go from 0 to 9. And then after each count, it's going to sleep for 100 milliseconds and then go back to the top of the loop and keep going until it's counted all the way up to the end. Then it's going to print out the process is complete and then the function will end. And then in our main function, we're going to print out the process ID for the main process. It's the process that starts the two subprocesses, and it's going to print out its own process ID for the sake of comparison. Then we create our two processes. By default, we really only need to specify the target parameter, which is just basically passing in the name of the function. And it's important to pass in the function without the parentheses. If you include the parentheses, it's going to just execute the function right there, and then it's going to store the result into target, which in this case will be none because we're not returning anything. So when you set the target, you put the function name without the parentheses. Then, if the function has any arguments that have to be passed in, we can pass in a tuple containing the arguments it will need into the parameter args. Since process count takes two parameters, name and count, we have to pass in two arguments here. So I pass in a string for the name and a number for the count. And then while they're running, the main process will also count to 10, or technically from 0 to 9, and then it will also print out each time it counts and then sleep for 100 milliseconds. And then once all that's done, we then call the join methods for both processes. Now with multiprocessing, and I believe multithreading as well, once they're finished with their execution, it usually ends and closes out on its own. If you were to monitor this in Top or some other process monitoring tool, you would see that all the Python processes for multiprocessing would disappear. So what's the point of join in this case? The point of join is to make sure that the main process does not die before those other processes have finished doing their job. This is particularly important, especially if, say, the subprocesses are printing stuff out onto the screen, and if the main process dies, sometimes that printing may not actually happen. So it's usually best practice, even with multiprocessing and definitely with multithreading, to always call the join method to have the program sit there and wait for the processes that it may have created to actually end. So I'm going to go ahead and run this first example here. As you can see here, we've got three process IDs and they're all different. Now, if you've seen the multi-threading video, then you know that when you have multiple threads running, they're all going to have the same process ID because the threads run under the same process. In this case, we're actually activating multiple Python processes to run these actions. So they're all going to have their own process ID. And then as you can see, they're all printing out their output, counting up to 9 and everything, and printing out their messages as soon as they can. And then the other difference between these two, although we can't really see it because it's more under the hood, is how the multiprocess runs as opposed to multi-threading. Multi-threading runs under the same process. So we can spin a whole bunch of threads, but it's still going to execute under the same Python process. And as a result, when they're doing their code executions, they have to take turns because it's constantly swapping out between the different threads for them to do a few code executions before switching out to the other one. Now, I don't know if printing actually counts for that because printing is technically a form of IO, so it may not be affected by the global interpreter lock. But it is a thing where they have to actually wait in line for it to be their turn to execute again because it's constantly swapping between the different threads. With multiprocessing, they're all basically doing everything at the same time. And when it comes to IO type stuff, especially like with printing, it's just a matter of who got there first. Now for this next example, I'm going to show you not only how to create a class that inherits from the multiprocessing process class, but also how to share information between processes. So let's start with sharing data. There are many ways to do it. Obviously, you can do stuff like file writing, network sockets, and maybe database stuff. There's tons of ways to do it. But I'm going to focus on two methods that are very specific to multiprocessing. In this example, we're going to use the queue. If you've seen my multi-threading video, it's basically like how I use those lists to share data with the threads. You could basically put data onto it from one process, and the other process that has access to it will be able to see it update in real time and get that data. So I have the doc handler class that inherits from process, and in the init, I have the parameters name, color, and queue. Name is just so the doc handler can identify itself when it's printing out onto the screen. Color is just so we can differentiate a little bit better between the two doc handlers that are going to be running. And queue is just basically how it's going to be able to reference the queue object that we create when we pass it into the object. And then of course, with multiprocessing, in order for it to be treated as a process object, we have to make sure it calls the supers init. Without calling the parents init, we won't be able to treat it like a process object. The other thing the class needs in order to operate as a process is the run method. We need to define any code that will be executed by the doc handler process under a method called run. For doc handler, the run method is going to run through a while loop. And as you can see, it's going to run infinitely. And it's going to retrieve data from the queue using the .get method. And when it does that, it's going to check to make sure that that data is not equal to EOF. If it is, it will break out of the loop so that the process can end. If it's not EOF, then it's going to come down here and print out the message, starting with its name and then printing out the data that it got from the queue. Then it's going to sleep for 100 milliseconds and then repeat the process. So that's how the doc handler is going to work. Now down here in main, we create our two doc handler objects. I name them doc1 and doc2. Doc1 will get light blue text color and doc2 will get yellow text color. I then also pass in the two queues I created up here. So I got doc1 queue and doc2 queue, and I give them to their docs respectively. Then I start them. And so now they're going to be running and waiting for something to happen for them to receive data through the queue. And then after I start them, I go through two for loops. They both go up to range 50. And in each for loop, for each increment up to 50 that is even, it's going to send a message to doc1. For everyone that is odd, it will send it to doc2. And we do that by just saying doc1 queue or doc2 queue dot put followed by the data. That will make it so that it's accessible to the processes that we run. So when they call queue.get, they will be able to see that data. So they do that up here, and the messages are just simple. Just ship X has docked, and each dock will print out that message. Then down here we'll say that each ship has departed. Then I send the EOF message to both queues, so that will close them out. And then I finally call the .join method to again wait for them to close out before letting the main process close out itself. So I'm going to go ahead and run the program. And as you can see, it's alternating pretty evenly between blue and yellow and doc1, doc2. That's really just because we're alternating pretty evenly with sending the data between the two queues. So we're not really going to see much of a huge variance in how the data gets printed out. It's going to be pretty much like this all the time when we run this program. But that's how you would send data between processes using a queue object. Another way we can send data between two processes is through a pipe. Now, a pipe is pretty much like a network socket. You get two connection endpoints that you set up, and then you can basically use them to trade information between two processes. So we've got two pipes, and each pipe will generate two connection endpoints, which I've named doc1_1, doc1_2 for the two endpoints for doc1, and then doc2 underscore 1 and doc2 underscore 2 for the two endpoints for doc2. The way the pipe works is that we have a receive function to receive the data, and we have a .send function to send the data. Doc handler is pretty much the same, except instead of passing a queue, we pass in a pipe. And the run method is pretty much the same as well. It just receives data, prints it out, and if it's an EOF message, then it just quits. Main is pretty much the same as well. We create the two doc handlers, and for the pipe, we give them the _2 connection point, and we hold on to the _1 connection point in the main. And when we go through the for loops, we basically say _1.send followed by the message. And it's pretty much dividing up the messages the same way as the previous example, where even numbered messages will go to doc1 and odd numbered ones will go to doc2. And then we send the EOF message and then we join them so that we can exit out properly. So I'm going to go ahead and run the program. And it's pretty much the same, except that we're using pipes. Now for this next example, we're going to look at pools. Now, unfortunately, pools is a little bit outside of my wheelhouse because I rarely use them. I've used them maybe once or twice. There's a lot of documentation out there that will advise you when it's best to use them and when not to use them. I would advise looking at that documentation. There's plenty of sites that talk about it and they really help determine whether or not a pool is right for you. I've used it maybe once, and I think that was just in school when I was first learning how to use a pool. But honestly, I don't see myself using them that often. It's not to say they don't have a use, it's just I've never had to use them personally that often. But I did still want to cover it just so you know it exists. So for this example, to access the pool, you can say from multiprocessing import pool, or you can just say import multiprocessing, and then when you call upon it, just say multiprocessing.pool. So there's no real right way to actually load it in. I've got three functions in this example, and we're not doing anything with sharing data, so there's no pipe or queue, just kept it simple. We got three functions here, process count, named process count, and main. Process count just takes in one parameter, it's count, and it's going to just basically count from 0 up to the number before the count that we specify. So if we specify 10, it'll be from 0 to 9. We just print out the message saying we counted to that number, and then we sleep for 100 milliseconds, and then once it gets that last number, then it leaves the for loop and quits the function. Named process count is basically the same, except when it prints out any of its messages, it will print out its name. Process count will just simply print out its process ID. And they all print out their process IDs too. So main's got its process ID, named will print out its process ID, and process count will print out its process ID as well. Main is not going to do any counting, it's just going to show you three different ways to handle a pool. So the first thing we're going to do is create our pool. Now we can just create a pool with no parameters if we want. That would basically put no limit as to how many processes it can run at a time. Really the only limit to that would be what your computer can handle. But in this example, I specify the parameter processes and I set it to 2. This means that only 2 processes will be able to run at a time. Now for the first example, I demonstrate the map method. The map method is ideal for functions that take in a single parameter. So we pass in the function name for the function we want to create multiple processes of, followed by a list of single values to act as the argument that will be passed into the parameter. So in this case, I'm passing in process count as my function. It takes a count, which is going to be an integer. So we pass in a list of 2 numbers, 10 and 20. So it will create 2 processes, one that will go from 0 to 9, and the other that will go from 0 to 19. In the second part here, I show you how to use apply async. Apply async is good for when you want to run multiple different functions in separate processes, as well as running functions that may have anywhere between 0 and whatever number of parameters to be defined to have values passed in. So in this example, I'm still using process count, so it's just going to be one argument. The arguments have to be passed in as a tuple. So if it's just one argument, then you have to add a comma so that it knows to identify it as a tuple. And then to get any output or results from those functions we run in the process, we have to store the asynchronous result object that we get from calling this function into a variable. And then we would call upon that variable's .get method to get that information. The timeout is optional. It just means that after 1 second, the subprocess will time out, or the receiving of the data will time out. And even though the execution of this looks like it's linear, it's not. It's going to basically still run as multiprocessing, so we're going to see everything get mixed up when it prints out onto the screen. And then this third part is still showing off apply async, but this time it's demonstrating how to run functions with multiple parameters. So I've got a list of tuples containing 2 arguments for our named process function, and I pass that into apply async for the named process count, and we add them to a list of tpool results. So we're going to have a list of asynchronous results. And then we loop through that list of asynchronous results, calling the .get method so that we can have everything print out on the screen. So I'm going to go ahead and run the program. So for the first part, where we just create 2 process count processes for 10 and 20, we see the 3 process IDs get printed out: 7248, 7249, and 7250. And then we see the 2 processes we created in the pool count to 9 as well as 19. Then for the second part, where we have 1 count to 5, 1 count to 6, as you can see, they're still pretty much printing the same way as 2 processes would concurrently. And you will also have noticed that they both have the same process IDs as our previous functions. Now, I don't know if that's because I specified 2 processes maximum for the pool, or if it's just something it does beforehand, but that basically means that it pre-allocated those process IDs beforehand so that only it can use those IDs. And then as you can see, it counted out its numbers up to 4 as well as to 5. And then here you notice that it also printed out none. With apply async, it will print out the return result of the functions we passed in. And since these functions don't have actual return results defined, it by default returns none. If I returned a number or a string or something else, it would print that out instead. And then for the third example, we have 3 processes getting ready to start. But because we only allow 2 to run at a time, the first 2 start immediately and they start counting. Only once one of them has completed will it be able to free up space for the third process to count. So they start counting, and then process 1 and process 2 completed. Process 1 completed first, so when process 3 started, it got process 1's process ID. And then process 3 starts counting, and then it completes, and then it prints out their return values, which again was none. So that's pretty much the basics of how you would use a pool. Unfortunately, I can't really go into more detail other than what I've presented so far because, again, I've never really had to use pools before in Python. I've never really found myself in a situation where I actually needed them. But I figured it was still good to talk about them for you guys so you at least know what they are. Alright, for this last example, we're going to cover one more topic, and that is the lock object. When it comes to multi-threading in general with programming, you will often have to control resources that might be shared between the different threads or the different processes, because if they try to access them at the same time, it can cause issues. To help control this, we utilize what's called a mutual exclusion lock, or most commonly known as the Mutex lock. With a Mutex lock, we can basically make it so that a process or thread can secure its turn to access something, allow it to do its stuff, and then release the lock so that another thread or process can have its turn and acquire the lock. In Python, with multi-threading, we don't really have to worry about that because we have the global interpreter lock. So it's pretty much got all that stuff built into it. It's not to say we can't still implement our own mutex locks with multi-threading. It's just most often than not, it's not really that necessary. When it comes to multiprocessing in Python, however, we don't have a global interpreter lock, so we have to explicitly create our own locks when necessary. And we usually have to do this when processes are trying to access the same file to read and write stuff to it. There could be a shared object in memory that they're both accessing, and if one is like popping stuff off of it while the other one is just trying to look through it and you throw off its index and it hits out of bounds, that can cause some problems as well. So there's many reasons why you should use a lock when you're using multiprocessing. Especially when you want to print stuff out on the screen and you want it to look nice and pretty, you might want to make it so that there's a lock that controls who's allowed to print out at the screen at a given time. And that's what we're going to be demonstrating in this example. We're going to just create a basic lock to control what doc handler is allowed to print on the screen at a given time. So for this example, I'm going to walk you through main first, and then we'll go back up to doc handler to show you what's happening. So in main, I create a single lock and I create a single queue. The lock is going to control who currently has access to the queue as well as who is currently allowed to print to the screen. So we give them both the same queue and we give them both the same lock. And what we put on the queue is a little bit more simplistic. Instead of putting whole messages onto the queue, we're just going to put numbers in the queue. And I'll explain why once we go back up to look at the doc handler. So we start both doc handlers, we just put some numbers on the queue, then we put 2 EOF messages. And that's going to be important too. I'll explain once we get up to the doc handler. And then once they're both done, we close everything out and then we end the program. So now looking at the doc handler, first let's look at our init. So we take in a name and color as usual. We have a queue so that they can access it and get the data. And then we pass in the lock. You also notice we have a list called pads. The doc handlers are no longer just going to be printing out messages. They're going to take the numbers from the queue and actually store them in a list to simulate that they currently have ships actually docked in the object. It's not just a message saying they're docked. And they will have a limit as to how many ships they can have stored in the pads list, which brings us down to the run method. So the first thing we do is we set a variable open to true. This is going to be controlling a few things, including what keeps the run method continuously running. First off, the while open. So as long as it's while open, it's going to keep looping through this whole while loop. Once open is set to false, it will break out of this while loop and then the process will end. Next, we have to acquire the lock. Now, if the lock is not available, it will wait until the lock is available. And there are 2 ways to do it. The first way is to say self.lock.acquire, and then once it's done, we say self.lock.release. We can also just use the with keyword and say with self.lock and then just put all the code we need to do while we have access to the lock. So that's what I do here is I just use the with keyword and say with self.lock. Then once we get the lock, I start printing to the screen because this lock is controlling my ability to print to the screen as well as access to queue. And so I'm going to make the printout look nice and pretty so we can tell the difference between what is doc1 output and what is doc2 output. So we print out a message saying docx updates. Then we check to see if pads is empty or not. If it's not empty, we pop a ship off the list to say that it's departed. And we only pop off 1 ship. Then we go down here to our while loop where we basically say, as long as there's space in the pads, add another ship. And we keep doing that until the list is full or we reach EOF. When we reach EOF, we set open to false and then we break from this while loop right here. Otherwise, we just add a ship to the list, we print out that that ship has landed, and then we keep going until we reach 6 ships. Once we get out of this while loop, we go down here and we check to see if open has been set to false. If open has been set to false, then we go in here and then we enter another while loop where we continue to pop all the ships off the list until that list is empty. Once all the ships are gone, then the dock can officially close down. Regardless of whether or not open is set to true or false, we go down here and we print out this little line here to indicate that the updates from this particular dock handler is finished. Then we print an empty line here and then we leave the with code block and therefore we have released the self.lock so that another process can acquire the lock. And once we do that, we sleep for 100 milliseconds and then we go back to the top and we wait for the lock to become available again. And the reason why we have to have 2 EOFs is because the only way to get information off of the queue is to pop it off the queue. So once one dock handler pops off the first EOF message, the other dock handler won't have an EOF message for itself. So we have to add 2 so that they can both get one. So I'm going to go ahead and run the example. And as you can see, we got doc1 updates and doc2 updates. They both initially fill out their landing pad with 6 ships. And then after the initial fill up, each time they send an update, it's to tell us that a ship has departed and that a new ship has docked. And they keep doing that until all the ships have been sent through the queue and the EOF messages have been sent. And then once they get down here, this is where they've received the EOF messages. So they start sending all the ships off, getting them off the landing pad, and then they close down. And then the program ends. So that's how you can use a lock to better control resources like IO stuff and just accessing certain objects that are shared between different processes. And that's about it for multiprocessing in Python. So I hope you've enjoyed this video and found it helpful, and if you did, then please hit the like button and leave a comment below to let me know what you think. And if you want to see more, head on over to Wayfair Coding Academy channel to check out my other content. And while you're there, subscribe to the channel to stay up to date on new stuff as it comes out. Thanks for watching, and I'll see you all next time.